Okay guys, today we're going to talk about chemical bonding. Valence electrons have a lot to do with chemical bonding. So, what are valence shell electrons? Valence shell electrons are the electrons in the outer energy level. Also, they are the electrons in the highest energy level that are in the S&P orbitals. For example, if an element is in period 5, that means its valence shell electrons would be in energy level 5 because 5 is the highest energy level and is the one farthest from the nucleus. Electrons are in the outer energy shell. Valence shell electrons basically are each of these. You may see them described as the outer energy level, electrons in the outer energy level, or the highest energy level, or the highest S&P orbitals, or in the outer energy shell. So how do you know the number of valence electrons that an element has? Well, if you think back to Unit 5, we talked about that. You look at the periodic table. Group 1 all has one valence shell electron. Every atom in Group 1 or element in Group 1 has one valence shell electron. Group 2, every element in Group 2 has two valence shell electrons. In general chemistry, first year chemistry, we usually don't look at the transition metals, so let's not look at these right here. Group 13, we're going to look at the number right before the A. Group 13 has 3 valence shell electrons. 14 has 4, 15 5, 16 6, and 17 7. Now 18, also known as the noble gases, they have 8 valence shell electrons, with the exception of helium, because helium only has 2 electrons, and since it only has 2 electrons, it can't have 8 valence shell electrons. It can have 2. Now energy level 1 can only hold 2 electrons, so helium has a full outer shell. So why do chemical bonds occur? Chemical bonds occur to achieve a full outer shell of electrons, or to obtain 8 valence shell electrons with the exception of helium. Helium only has 2. To look like a noble gas. Now remember, noble gases are inert, or they are stable, which means they do not react. Chemical bonds occur for elements to become stable. What is the rule? The rule is the octet rule. OCT means 8. Oct means 8, like octopus has 8 legs. Octagon has 8 sides. You'd think that October would be the 8th month, but it isn't, so I don't know what the deal is with October. But octet rule means it has 8 valence shell electrons, or 8 electrons in its outer energy level. So what group of elements will the bonded elements be like if they have a full outer shell? Well, let's look. A full outer shell, that would be 8 valence shell electrons, and that would be group 18. What is group 18 called? They are called the noble gases. So every bonded element will look like a noble gas. So now let's practice. How many more electrons does fluorine need to have a full outer shell? Well, here's fluorine. It is in group 17, which means it has 7 valence shell electrons. Now it wants a full outer shell, which means it has to lose all of its valence electrons, and if it loses all of them, it wraps back around and looks like helium, so it would have to lose 7. Or it could just gain 1 and look like neon. And it's much easier for fluorine to gain 1, so that's what it will do. It will gain 1 electron. Okay, so what about phosphorus? Phosphorus is right here. It is in group 15, which means it has 5 valence shell electrons. Now it can lose 5 to have a completely empty outer shell and look like neon, the noble gas neon, or it can gain 3 electrons and look like the noble gas argon. It is much easier for phosphorus to gain 3 than lose 5. So that's what it will do. Phosphorus will gain 3 electrons. So why do group 18 elements do not want to bond with other elements? Group 18 has 8 valence shell electrons, and that's stable. If they add any more electrons, they will no longer have 8 valence shell electrons, and they will bond until they do. If you take away any electrons, group 18 will no longer have 8 valence shell electrons, and they will bond until they get it. That's why group 18 elements do not want to bond with other elements. They already have a full outer shell. Okay, number 4. What type of electrons are involved in bonding? That would be the valence electrons. Okay, we have 3 types of bonds. The first one is the ionic bonds. The ionic bonds is an electrostatic attraction between cations and anions. Cations are positively charged and anions are negatively charged ions. Cations give away electrons, making them positively charged, and those are typically metals. Anions take away electrons from other atoms, making them negatively charged, and those are typically nonmetals. Ionic bonds typically happen between metals and nonmetals. Okay, now let's look at this ionic bond here. We have lithium atom. It has 1 valence shell electron. Now remember, it wants a full outer shell, so in order to do that, it would have to gain 7 electrons or lose 1, and it would be much easier for lithium to lose 1. Fluorine over here has 7 valence shell electrons. It also wants a full outer shell, and in order to do that, it would have to have a completely empty shell, which would mean that it would lose 7, or a completely full shell, which means it would need to gain 1, and that's exactly what it does. Fluorine is a highly electronegative atom, if you remember from your periodic trends, which means it attracts electrons. So it will pull off that electron from the lithium atom. And when it does that, lithium now has 1 less electron, so it has 3 protons and 2 electrons, which means it has 1 more proton than electron, which makes it a positive charge. Fluorine has 9 protons, and now it has 10 electrons, which means it has more electrons, which means it's a negatively charged. Now these 2 ions have opposite charge, and they also have an electrostatic attraction between the 2 of them. So they are attracted to each other, and that's what makes the ionic bond, this electrostatic attraction between the 2. This is an electrostatic attraction here. Okay, now let's look at sodium and chlorine, sodium chloride. Sodium has 1 valence shell electron. It needs to either get rid of all of its electrons in its outer shell to become stable, or gain enough to make 8. So it either has to lose 1 or gain 7. Sodium would rather lose 1. It's much easier. Chlorine has 7 valence shell electrons. It either needs to lose all 7 or gain 1. So it will gain 1. It's much easier. Now chlorine is a highly electronegative atom. It's highly electronegative, which means it can attract an electron very well. And that's exactly what it does. It takes sodium's outer shell electron away from it. And when it does, sodium becomes a positively charged. It lost 1 electron, so it becomes a positive 1. Chlorine gained 1 electron, so it becomes a negative 1 charge. And since positives and negatives attract each other, it's called an electrostatic attraction, then they become bonded, and that is the ionic bond. Now covalent bonds, let's talk about them. Have 2 or more highly electronegative atoms, which means neither one of them want to give up an electron. So they have to end up sharing electrons. This is typically between a nonmetal and a nonmetal, because remember, nonmetals are on the right-hand side of the periodic table. And if you remember your electronegativity trend, nonmetals are highly electronegative, or the right side of the periodic table is. So now let's look at 2 hydrogen atoms. Now I'm only going to show the valence shell electrons, okay? So this hydrogen has 1 valence shell, this hydrogen has 1 valence shell. Hydrogen is a nonmetal, so it does not want to give up any electrons. What's going to happen is it wants to look like helium. It wants to gain 1 more electron because helium has 2 electrons, and helium is a noble gas. And in order to do that, it is going to share electron with each hydrogen. So right here we have a shared pair. This is a shared pair of electrons. And one shared pair of electrons equals a bond. It is a bond. So right here we have a single bond. And this is what a hydrogen looks like. We denote a single bond with a line between the two. It is not H minus H. It is hydrogen single bonded with another hydrogen. Next example, we have fluorine. Fluorine has more than 7 electrons. I am only showing the valence shell electrons here. Now, they can lose 7 or gain 1. They would much rather gain 1, but neither one is going to give away any electrons because they are highly electronegative, which means they're going to share. And when they share this one pair right here. And that is what denotes the bond. So this is what the fluorine looks like. Fluorine single bonded to fluorine. Now let's look at carbon dioxide. Oxygen has 6 valence shell electrons. It wants 2 more. Carbon has 4 and it wants 4 more. So oxygen is going to have to borrow 2 from carbon. Now let's rearrange these so we can make that happen. Now when we do this, carbon has moved its electrons over here so oxygen can borrow, and oxygen has moved its 2 electrons over here so carbon can borrow. Now if we look here, right here, this oxygen has 8 valence shell electrons. So it is a very stable element now because it's bonded. And this carbon right here has 8 valence shell electrons. It is very stable as well. Now let's look. Remember what I said. A bond is equal to a shared pair of electrons. Let's see how many shared pairs we have. We have 1, 2 between this oxygen and this carbon, and we have 1, 2 between this oxygen and this carbon. So what this looks like is carbon double bonded to an oxygen on each side. This does not mean oxygen equals carbon, which equals oxygen. It means oxygen double bonded to carbon, double bonded to oxygen. Now, again, we have carbon that has 4 valence shell electrons, and each fluorine has 7. None of them are willing to give it up, so they're going to share. And when they do, each fluorine atom is going to have 8 valence shell electrons, and the carbon atom is going to have 8 valence shell electrons. Each one of these denotes a shared pair of electrons. So if we were going to write this out, it would be carbon single bonded to a fluorine, single bonded to a fluorine, single bonded to a fluorine, single bonded to a fluorine. Now here we have 2 oxygens and they each need 2 electrons. So let's rearrange this so this oxygen can share 2 electrons with this oxygen, and this oxygen can share 2 electrons with this oxygen. And once we do that, we will see that each oxygen has 8 valence shell electrons. The electrons that are between the 2 atoms are the pairs that are shared. And that is what creates the bond right here. So it would look like oxygen. This is a double bond oxygen because there are 2 single bonds or 2 pairs of shared electrons. These electrons right here and right here on each oxygen are not involved in bonding at all. They stay with each of their respective oxygens. They're not shared at all. Okay, now let's look at nitrogen. Nitrogen has 5 valence shell electrons because it is in group 15. It needs 3 more. So it will rearrange its electrons so that it can share 3 with the other nitrogen. And if you notice here, each nitrogen has 8 valence shell electrons. There are 6 here and 2 here, which makes 8. And this nitrogen has 6 here, and 2 here. These are our shared pairs. These are our shared pairs right here in the middle, and we have 1, 2, 3 shared pairs, which means we have a triple bond because we have 3 bonds. What this looks like is N triple bonded to another nitrogen. Now on metallic bonds, I am going to let another chemistry teacher, Mr. Joel Weiner, explain this to you.
Okay, this is a tutorial on metallic bonding, and we're going to be looking at the Electron See model of metallic bonding and how that can explain such properties as malleability, conductivity, and so the properties of metals can be understood by looking at the atomic structure of metallic bonding. But first, let's get reacquainted with the ionic bond, because if you understand the ionic bond, that's going to make it a lot easier to understand what the Electron See model is telling us. So here we have a metal reacting with a nonmetal. The transfer of the electron, the reaction, results in a positive ion and a negative ion. So the ionic bond is simply the electrostatic attraction between the positive and negative charge that the ions have. So you could call this a sodium atom and this a chlorine atom, and once the sodium loses an electron, it becomes Na+, and the chlorine gains that electron and becomes Cl-. So the sodium ion and the chloride ion, being oppositely charged, are electrostatically attracted. And so that opposite charge results in a crystalline structure where we have an ongoing array of alternating positive and negative that are all attracted to each other, and that keeps the crystal together. Let's look at the arrangement of atoms in a metallic crystal. Very similar to the organization of an ionic crystal, however, they're all positively charged. And just looking at this illustration, you would think that the atoms would completely fly apart by repelling each other due to the positive charge. But if we take a closer look, the Electron See model tells us how the positively charged cations in the metallic crystal can stay together. So as an example, we'll take a look at aluminum. Looking at the subatomic structure, we can see each aluminum atom has 13 protons, but only 10 electrons. It has given up the 3 valence electrons to what is called the Electron See. This is why it's called the Electron See model. The space in between each atom is filled by the valence electrons that have been given up by each metal atom. So the metal atoms become cations, positively charged ions, and the valence electrons are loose in the spaces between the cations. So what's holding the crystal together is the electrostatic attraction between the positively charged cations and these free-floating negatively charged electrons. And so the valence electrons are not localized to any one particle. They are free to move and occupy the space between the positive ions. And so similar to the electrostatic attraction that holds the ionic crystal together, we have this attraction of opposite charges that are holding the metallic crystal together. So aluminum giving up 3 electrons means that all the cations have a 3+ charge, and each aluminum atom has contributed 3 electrons to the sea of electrons. This creates quite a strong attraction, and we can use this model as a way to explain various properties. For example, there is malleability, the ability to put pressure on a piece of metal and not have it break. So we can pound metal with a hammer, we can pound it into a shape and not have it break. How can this model explain that phenomenon? Well, let's hit it with a hammer and see what happens. Ooh. One last blow. Okay. So as you can see, the atoms were shifting. They didn't break apart. Hitting the metal with a hammer does not break it. Why would that be the case? Well, the delocalized electrons are always there. So any shifting positive ions are going to be able to be held together by their attraction to the constant presence of those valence electrons, that sea of electrons that the atoms are attracted to. And malleability, of course, is also intimately related to ductility. You can force the metal into the shape of wires. So this is malleability. And a nice contrast would be to look and see, why does hitting an ionic crystal not result in this sort of malleability? When we hit an ionic crystal, it shatters. Let's hit this ionic crystal with a hammer and see what happens. So no matter how you hit it, you're always going to come to some point where like charges are lined up. And so if like charges are lined up, the result is going to be a great deal of repulsion, and that's going to split the crystal. And when ionic crystals cleave, they often leave a very sheer, smooth face if you do it carefully because of the way the opposite charges line up. All right, back to metallic crystals. So why would this very strong attraction result in other properties? How about their strength and high melting point? Well, the atoms want to stay together. They're very attracted to the sea of electrons. And so therefore, the higher the amount of valence electrons given to the sea of electrons, the tougher the metal, the harder it is, and the higher the melting point. Transition metals in particular, like titanium and molybdenum, each of which contribute to large amount of valence electrons to the sea. They are very tough metals, very strong, very high melting points. How about electric current? Can this model explain that? Well, electric current is simply the movement of charge, and electrons are constantly moving through these spaces between the cations. They therefore are very able to carry an electric current, and that also explains their heat conductivity, the fact that they can move through the crystal.